Okay, so our quiz was write this equation in logarithmic form, write this equation in exponential form. Then if you got it, I said, go ahead and solve it. One of them's easy to solve. One of them, they're both easy to solve. But one of them's a little more obvious than the other because the symbols look easier. Okay. Well, this equation is this in logarithmic form. That's it. Okay. Now, most of you still need to go back to the rules. You don't have to write them out the way I do. Open Math probably showed you how they write it out. There's no ideal notation. But I like this notation, but you can use whatever notation you want as long as you have it right. Okay, so in my notation here, this is in the second form. So this equation is form given C equals A with what? B is the things being raised to a power. B is 2. 2 is what's being raised to a power, right? And C, well, C is the exponent. What's the exponent? The exponent's x plus 4. And that was a little curveball because I don't think you had anything like an x plus 4 for an exponent in most of the problems you saw. But if you follow the procedure and keep your wits about you, it just falls right out. Okay. And then A equals 9. So here's B. Here's C. Here's A. Well, this is then going to be of the form log base B of A equals C. Okay, and we've already identified A, B, and C, and we say that these are equivalent. They have exactly the same solutions. Okay, so B is 2. So what right there is B. Log base B of A, well, A is what you're taking the log of then. So here's A. And over here is C. Okay. That's all there is to it. Now you know that if you've done the homework, you know it's easy to reverse these when you got the rule in front of you, but when you have to think of the rule and then apply it, well, that's what you try to prepare yourself to do when you come into class, okay? Because that helps you lock it in, and it's the procedure you need in order to prepare for an exam, which I have in a couple of weeks, okay? Now that can be solved, but we'll just move on. All I asked you to do was change the form. So there's your equation. And there it is in logarithmic form. This equation is in this form. So we write log base 2 of x squared plus 6 equals 3. Well, that's form log base B of A equals C. Okay, and what's B? Well, it's log base B, it's log base 2. So B's got to be 2. A is what you're taking the log of, that's x plus 6, x squared plus 6. And C is what's on the other side of the equal sign, that's 3. All right. So you write this in this form. going to be put into the form b to the c equals a. And that gives you b is 2, c is 3, a is x squared plus 6. Okay. So again, here's b. Go ahead and draw an arrow down through there. Here's a. And here's c. And here's b. And here is c. And here's a. Okay. Now let me go ahead and actually solve these equations. Okay. Don't have enough room. Here. No, that's not funny. Okay, come on now. Oh, that's a small format. Where's the other? Maybe I'll hide my board. Okay. Okay, I'm dead in the water there. Okay, come over here. All right, so let's write out the equation. And now that I've got these boards messed up, I'm going to be tripping over them. As I said, I'm not completely with it today for some reason. Weather, I don't know, no good explanation. Okay. Chalk. Bigger piece right here. Okay. Okay, so we got the equation 2 to the x plus 4 equals 9. Using our equivalents, we can write that as log base 2 of 9 equals x plus 4. What do we have to do to solve this equation for x? Well, we've got what x plus 4 equals. We just subtract x from both sides. So we get x plus 4. And I'll write the x plus 4 on the left side and the log base 2 of 9 on the right side. So yeah, I just reverse the two sides, and I subtract 4 from both sides, and that gives me x. That's all there is to it. Now, of course, you take your equation. I mean, if you want to solve it, you're going to have to use your calculator, right? But this is the solution. If you want the decimal equivalent, then x equals log of 9 over log of 2 minus 4. Okay. Now, log of 9, well, log base 2 of 9 is just a little over 3. It's about 3.1 or so. 3.1 something. Okay. Maybe close to 3.2. Your calculator will give you a very good approximation. Won't be exact, but it'll be a good approximation. And so that one's not hard to solve if you just remember that this is just a number that you don't know. Okay? It's not an unknown, it's not a variable. It is a definite number that your calculator will approximate. Okay? If you remember that log base 2 of 9 is log 9 over log 2, and that's one of the two rules that we emphasized last time. So you want to have that straight. Okay, for the second equation, okay, that's equivalent to the third equals x squared plus 6. Make sure I'm writing that in the same order as before. Okay. Well, 2 to the third is 8. So 8 equals x squared plus 6. So x squared plus 6 minus 6 equals 8 minus 6. So x squared equals 2. So x equals, now nobody really got this completely right. X can be plus or minus 2. If you square the square root of 2, you get 2, right? But if you multiply negative square root of 2 by negative square root of 2, you get 2 again. Okay? Then you've got to understand that. Because if you start missing solutions, you might miss the solution you really need. Get it very easily. This is actually a quadratic equation. You could have used the quadratic formula. It could have been x squared minus 2 equals 0. So A would be 1, B would be 0, C would be minus 2, and you plug it into the formula, and you would get 2 solutions. Okay. So make sure that we're good with this because we've got to go on with some more rules for logarithms, okay? Oops. Okay. So, more rules. Log of A times B is a log of A plus the log of B. Now this is inverse to the rule. Now, what is the rule of exponents for x to the a plus b? What does the rule of exponents tell us x to the a plus b is equal to? Can you write that down on your paper? Just to see how familiar are you with the rules of exponents, because it's extremely important to be familiar with them. Okay, now people are not doing well with the rules of exponents. Very, very important. So let's just take the example. What is 2 to the 3 plus 4? Well, really make sure you've got this. 2 to the 3 plus 4 is, of course, 2 to the 7th, isn't it? And what's 2 to the 7th? Well, you can write out it's 128, okay? But that's not what I want to know. I want to know what 2 to the 7th means because I want this to apply to any x, not just to x equals 2 and a equals 3 and b equals 4. We want to see what happens with 2 to the 3 plus 4. And we get 2 to the 7th, which is, we don't need some really big numbers because we don't want to be writing these things out for a month, but there's 7 of them there, right? And of course that equals this. I can group this any way I want to. Okay. So if I've got 7 2s, I can group them into 4 2s and 3 2s, right? Or could I group them into 6 2s and 2 2s? Okay. But nobody wears 2 2s anymore, so we're not going to do that. Okay. Okay. Many ways I could group them, but this way is important for this because this shows you that this is 2 to the 4th times 2 to the 3rd. Okay. Now I think if I'd written x to the a times x to the b, you might have gotten it. And I'm pretty sure if I'd have written 2 to the 4th times 2 to the 3rd, you probably would have gotten that. Okay. So you're not far from this rule. But if you can't see, if you don't know this rule, you're always going to be very vulnerable to fatal errors, okay? Because it comes up all the time. We use it all the time. This is just an example that shows why this works. It's just one example. It doesn't prove the rule, but it's an important plausibility argument, and it works. Okay, if you can reason this out, then you know that this has to be true. Okay. Now, what about this one? Well, what's 2 to the 3rd to the 4th mean? Okay, just using 2, 3, and 4 again. Well, multiply 2 to the 3rd 4 times, right? 4 terms, or 4 factors, each one being 2 to the 3rd. Well, this gets a little long. So I probably should put the equal sign way over here somewhere. This equals well, 2 to the 3rd is 2 times 2 times 2, right? And I've got to have 4 of those just to write out what I've got here. So I've got to have that, this, and this, and this. Okay. Now, how many 2's am I multiplying here? Well, that's 12 of them, right? I'll write them all out. I think I've got them all. I can count them. There should be 12 of them because there are 4 of them. Sorry, there are 3 of them in each group, and there are 4 groups. That's going to be 12 factors of 2. So that's 2 to the 12th. So two to the 3rd raised to the 4th is 2 to the 3 times 4. Why is it 3 times 4? Because we've got 4 groups of 3. And if you write it out this way, it becomes clear why the rule is what it is. That's x to the 3 times 4. X to the a times b. Told you I'm not doing well today. I feel fine, but something's not connected. Okay, x to the a times b. Make sense? It's got to make sense. You got to understand it. And if you understand it, then it's easier to understand these rules because this rule is inverse to this. In what sense is this inverse to this? Well, here you're adding your exponents and you're multiplying the numbers, right? Here, the numbers are multiplied, but you're adding the logs. Okay? So what you do with exponents is inverse to what you do with logs, and you might want to think about that. Okay? It's just inverse to this. The reason for this rule is this rule. I'm not going to go deeply into that, but there's a relationship there that might help you remember this rule if you know this rule. It might confuse you, and if so, don't bother looking at the inverse property. Just memorize the rule and practice using it so that you get it right. Okay. Now, the inverse to this rule is the log of a raised to the b is b times the log of a. Again, notice that you're multiplying your two exponents here, just like you're multiplying b by log of a. And you have a power here. So again, without drawing all the parallels and proving it, which is a little complicated. We got this. Now there's another one that's really follows from these two rules. It's always stated as a separate rule, which I've always found ridiculous, but there's a reason for it because not everybody finds it ridiculous, okay? But the log of a divided by b is the log of a minus the log of b, okay? Now, usually this one's stated along with this one. But if you combine this one and this one, you get this one. And this one seems to be redundant, but still. Those are three rules. Then we're going to see how to apply them. Halfway make sense? Well, it doesn't really make sense to start using them. But at least you see what the rules are. So let's practice using the rules. What's the log of x squared times y cubed? Now it turns out that two rules are applicable here, but one rule really probably needs to be applied, but I think definitely needs to be applied first. So which rule is the most obvious one to use here? Okay, so we have log of x squared times y cubed, and we see that we can apply this. Well, this would be this with a equal to x squared and b equal to y cubed, right? So we could even make a note. I'm going to lose it. Good thing I saw that early. If I'd had to move any faster, it would have been a sonic boom. Okay. Not a good thing in a closed room. Okay. Pressure wave, it can damage your lungs. Okay. This is first rule with a equal to x squared and b equal to y cubed, right? So we're going to replace a with x squared. We're going to replace b with y cubed. That's going to give us the log of x squared plus the log of y cubed. Okay, can you read what I did? Because I had to compress it a little bit. Make sure those rules are, yeah, they're visible. Okay. Okay, now what can we do with the log of x squared? There's a rule that tells us we can do something with log of x squared, right? So see if you can write out what that gives us. Okay, well now log of x squared, well log of a to the b is b times the log of a, right? This tells you if you got an exponent here on this term, you can bring that exponent out in front, can't you? Okay. So log of x squared is 2 log of x. And this is that's because of the second rule with a equal to x and b equal to 2, right? Because a equals x, you got log of x, whatever b is, but b is 2, so that's a log of x squared. So that matches this. And that's equal to b times the log of a. And b is 2, and a is your x, so you get 2 log of x, okay? Whatever way you see that, that's what the second rule tells you. And then, if you see that, you're probably going to see that the same rule tells you that's equal to 3 log y. Okay? Make sense? So you got to see the rules. So we're just getting our feet wet here. Let's try this. What would you do with log of x plus 6 times x minus 2? Might be a little bit of a stretch, but let's see if we can do that. Okay, so looked like just about everybody got the first step and took the appropriate first step. You saw that this is a division, so that this rule applies. Okay, so you've got that this equals log of x squared y cubed minus a log of z to the 5th. Okay, I'm happy to see that. This is starting to make sense to everybody. And it's just a matter of practice. You know, it almost becomes a reflex. By the time you've completed the assignment, you'll be pretty secure with these, but you don't want to forget them the same way that people always tend to forget the laws of exponents, okay? You never want to lose track of it because it's going to come up again and again and again. All right, well, we'll just continue this here because now we can apply the rule to this, right? Apply the first rule here. Let's just do that. That's going to be the log of x squared plus the log of y cubed minus the log of 2 to the 5th. And I think everybody understands, if you understood this, you understand that. That's a product, right? So we just apply the first rule. Okay, well, what else can we do? Well, we haven't applied the second rule, but clearly it applies, right? Now, usually we've got to do the first and the third rule, whichever, this rule and or this rule before this rule is going to apply. Okay. So this is then 2 log of x plus 3 log of y minus 5 times the log of z. Okay. Now sometimes this is the form you want, sometimes this is the form you want. Okay. You can write, well, let's just do it. Okay, now try this one. What can you do with the log of x plus 4 log of z? Okay, now there are a couple of different things you can do here. A lot of people, well, saw that the second rule applies because you got 4 log z, and that's going to be the log of z to the 4th because of this rule. So that's perfectly good because you got two choices of what rule to apply. Okay, you've got a multiple of log z, and you can apply this rule. Another way to see it is you got a sum of logs. Well, if you got a sum of logs, it's going to be the log of the product, right? So the log of the product is the sum of the logs, and the sum of the logs is equal to the log of the product. You look at it this way or this way. And everybody did it at least one of the two ways, and a lot of people did it both ways, or saw it, or so, you know, saw both applications. So we can say that this is the log of x plus the log of z to the fourth by the second rule. And then by the first rule, this is equal to the log of x times z to the fourth. Okay. And actually, we do have to apply this rule before we apply the sum, because this rule doesn't have a 4 in front of your log of z, right? There's no number in front of either of these logs. So if there's a number in front of the logs, we've got to make it a power. And then we can do the sum. Now, if you understand that, you're ready to dive into the assignment, okay? The first assignment, there are two assignments that are coming up, so we want to look a little bit at the second one as well. Okay, switching gears a little bit, we're going to talk about graphs of logarithmic functions. Over just a bit. Okay, so first of all, we know what the graph of log base 2x is. So without going into a lot of detail, not particularly well drawn, but there's a graph of our base 2 log function, which we get by switching the columns of the basic exponential function. Okay, we'll use that as an example. A couple of things we want to observe about this graph. Well, let's do some transformation. So this is log base 2 of x. Can you graph for me? First of all, sketch this graph, and then graph log base 2 of x minus 1. Based on this graph on the same set of coordinate axes, show me how this graph is obtained from this graph. And we're back to transformations. We have to understand transformations in order to do this assignment. Okay. Compared to y equals log base 2 of x. X is replaced by x minus 1. And that shifts the graph 1 unit to the right. Okay, plus 1 unit in the horizontal direction, right? So each of these points moves 1 unit to the right. Take an arrow 1 unit long, and you take each point and you apply that arrow to the point. We call that a vector. A vector is something that moves something from here to there. Okay, use this 1 unit vector to the right. It moves each point 1 unit to the right. Just draw the arrow on each point, and it'll work on all the other points. Okay, doesn't have to be necessarily just the points you use to plot the graph. Every point is going to move to the right 1 unit. And this gives you log base 2 of x minus 1. Now notice an important thing here. You have a vertical asymptote here at the y-axis. That is, just like the exponential function approaches the x-axis as you move to the left, when you flip it over and invert in a certain way to get the log function, you're going to have an asymptote with a negative y-axis. So you're going to have an asymptote here. Note that x equals 1 is a vertical asymptote. This thing will be approaching x equals 1. It'll never go past it. It'll just keep getting steeper and steeper. Okay. Okay. Okay, well, let's try another one. What's 2 log base 2 of x look like? Okay, I think people are having a little trouble with this. Here's my hint. Compared to y equals log base 2 of x, what happens here? Well, your y values for given x are always going to be twice as big, right? So what happens is for each x, for each x, y is doubled, right? So pick a point on the graph. What happens if x stays the same and y is doubled? Where does that point go? Well, for each x, y is doubled, right? So let's pick an x. Let's not pick x equals 1, because for x equals 1, y is 0, isn't it? And if we double 0, we still get 0. Okay. Well, I want to construct this in a different color so we don't get things too confused. But, okay, well, if we pick this point and double the value of y, we're still on this point because y is 0. Now, if we pick this point and double y, well, y is equal to 1 here. If we double that, what do we get if we double 1? I'm confused today. Somebody hold up fingers and show me. Yeah, we get to. Okay. And everybody knows that. Now, x doesn't change. X is still, if X is 1, in this function, Y is 1. In this function, if X is 1, Y is going to be 2 times. Okay. Well, that's it. Let's say X is 2. Okay. If X is 2, Y is 2 here, right? If X is 2 here, well, the log of 2 is 1, right? Basic, basic log. And you multiply that by 2, you get 2. So X stays 1, Y goes from 1 to 2. Y gets doubled. So you're going to have a point there. If X is 4, Y is 2. If you double that, you get 4. And of course, if X is 1/2, Y is -1. If you double that, you get -2. So this point moves down here. This point moves up here. This point moves all the way up here. And this point moves further because you're doubling its distance from the x-axis. And this point goes way down here, so I'm not going to draw it. The graph stretches out, doubles in the y direction, okay? Now we're out of time. Your problems are going to, and Open Math is going to continue to explain how transformations work and how they apply to graphs of logarithmic functions, okay? And you really want to continue getting better at seeing transformations and how they behave with graphs of functions, okay? We've been dealing with this since the beginning year. It's always tough. I don't know why. It's always tough for pre-calculus students to master the whole idea of transformations. But if you do, and you're in my flat calculus course in the fall, you're going to be glad at some points that you understand these things, okay? Because there are certain rules for calculus that are easy to understand if you understand transformations, okay? And they're not impossible to understand if you don't, but they're easier to understand if you understand transformations.